All right. So today I'm going to talk about something that the Julia GPU community has been working for a couple of years on, and that's the ability to write portable code for a bunch of parallel accelerators in Julia. Before delving into that, I think it's maybe worth to decompose that title a bit. So portable probably means a lot to many of you, that the ability to write code and run it on a variety of platforms with a variety of processors without having to modify your code significantly, ideally not modify it at all. Parallelism requires a bit of nuance because it's often confused by people between concurrency and parallelism, where concurrency basically only means that you have a bunch of independent tasks that can run independently from one another, so that one task doesn't require the other to finish, while parallelism means that they actually execute simultaneously, which typically requires multiple cores in your system, multiple threads of execution. And that will have implications on how we write code. And the fact that we want to do all this in Julia is the obvious one, otherwise you wouldn't be here. So the reason parallelism is relevant to look at nowadays is because parallelism is essentially everywhere. Both if we look at the software we have nowadays, of course the whole AI and machine learning craze is extremely parallel. It's been written with GPUs in mind. Scientific software nowadays as well, highly parallel because it's dealing with lots of data. But day-to-day software as well, like games or web browsers, have becoming more and more parallel. And this is, of course, because the hardware stack has become increasingly parallel as well. Many of our hardware nowadays contains multiple cores and as a result can be programmed with multiple threads. The obvious example is the high-end supercomputers, which contains thousands upon thousands of GPUs, and they, of course, fuel the machine learning training that happens. But even day-to-day laptops and desktops have been shipping highly multi-core, highly parallel hardware for years. Phones as well nowadays, parallel hardware that seem asynchronous. And even if we look at the complete bottom end of the stack, this tiny Raspberry Pico here costs $5 and it contains 2 Cortex M0, so it can be used to do parallel programming with multiple threads of execution. And there's a reason, of course, for all that parallelism, and that's in a nutshell. Because we don't get to see the huge improvements of single-threaded performance anymore that we used to see before the turn of the century. So there used to be a time where we could just wait a couple of years and our software would magically become twice as fast because the underlying hardware became much faster. Until the turn of the century, it wasn't extraordinary to see a 50 to 60% year-over-year improvement of single-threaded performance, which is crazy thinking of it nowadays. All of that was based on 2 laws. It's Moore's law, which dictates how transistors increases, and the Denard scaling law, which regulates how if we scale down our transistors, we can raise the frequency without increasing the power consumption. And again, around the turn of the century, that started slowing down. You can see that the year-over-year improvement slowed down to about 10 to 20% a year. And nowadays, we can be happy if single-threaded performance increases 3 to 5% every year. And you can clearly see the end of those scaling laws on that other chart where, again, at the same point in time, all of a sudden frequency stopped increasing. And similarly, single-threaded performance doesn't increase exponentially anymore that much. But you can still see the transistor budget going up. So the question is, where are these transistors being put in? And then obviously at the bottom, you can see that the number of logical cores is also increasing by a lot. So with modern multiprocessors, we have much of our transistors being put into additional logical cores. So as a result, we actually do have to write parallel code if we want to use these new contemporary processors to their fullest extent. So that's the hardware side. At the requirement sides, some things have changed as well. One of the bigger changes is just the amount of data that we're processing nowadays. This is a very a summarized overview of the latest machine learning models. You can clearly see the AI boom at which point we started requiring much more massive amounts of compute because the data we're processing has gone through the roof, basically. And those kinds of compute requirements are very hard to satisfy with non-parallel hardware, especially when we also take into consideration the energy efficiency, because parallel hardware similarly tends to be much more energy efficient. So that small table, I collected some compute efficiency data expressed in gigaflops per watt, comparing contemporary modern parallel hardware such as an NVIDIA 8100 or a high-end Apple GPU with some very high-end CPUs, which can also execute multiple threads of execution in parallel, but nonetheless doing so at a much lower compute efficiency. So taking that all at face value, the conclusion is basically that parallelism is inevitable. We have to consider writing parallel code because our hardware is made for it and because our software requires it. But then the problem is that writing parallel code is tricky, it's hard. And as a running example, I'll be using, initially at least, the very embarrassingly parallel example of vector addition, where we have two vectors, A and B, of 1024 FP32 values, and we want to add those together. And as an example, I want to execute that on this laptop here, which contains an M3 CPU, which has a variety of programmable accelerators. There's obviously the CPU, which is a 16-core CPU, also containing a 128-bit wide vector engine. There's the GPU, which has 40 cores and curiously takes up much more die space. There's the MPU, which is a neural processor by Apple, proprietary. And there's the AMX, which is an Apple matrix accelerator. So if we want to try and run this simple vector example on any of those, starting with the CPU, we can obviously do a simple for loop, iterating over all values. It's an embarrassingly parallel example, meaning that there's no dependencies between the individual iterations, there's no communication necessary, meaning that we can also very simply parallelize it across CPU threads by using the add threads macro from Julia's excellent multi-threading support. That's easy enough. Moving forward, let's use the vector engine that's part of our CPU. We can pray that the compiler does it for us, which LLVM will occasionally do. But if we want to be explicit, we can use a package such as simd.jl. And here you can see that our elements-based for loop has transformed into a chunk-based for loop, where we're processing multiple sequences of elements at the same time. And the chunk size has to be chosen in function of the width of the vector engine. And in this case, it's 128-bit vector engine. We're processing FP32 values, so we can chunk with a loop stride of 4. Still reasonable. So let's dive down and try to use the AMX, which is a matrix accelerator. It doesn't support vector addition, but it does support FMA. So we can try and rephrase our problem in terms of an FMA operation. Sadly, we don't have any high-level either LLVM or simd.jl support, so we have to use this lower-level package called AMX base, which is a Julia package, exposing all of the low-level instructions of the AMX. And we can manually load data in X, load data in Y, load once in Y actually, load data in Z, perform the FMA, and fetch the result. Still reasonable, I guess, but it's becoming clear that this is not tenable. And then, of course, if you want to use a GPU, it's a completely different thing. All of a sudden, there's no for loop anymore. There's a scalar kernel, and we have to launch this in parallel using an otherwise unknown macro. So it's obvious that even though this is a very simple, embarrassingly parallel example, the fact that for this single processor, for the single chip in my laptop, we have to use 4 completely different snippets of code. Not portable at all, and as a result, very hard to write efficient parallel code. And this is even only considering what's available in Julia. If we actually have a look outside of Julia, you can see a whole bunch, hundreds literally, of parallel programming libraries and framework, depending on what hardware you're using, whether it's vendor agnostic or not, whether it's distributed or not, depending on what kind of abstraction you want, whether it's message-based or a global address-based. It's a mess. It's basically a mess. And on top of that, parallel programming is also hard in terms of how you write your algorithm. The vector addition was simple because it's embarrassingly parallel, but if we do something that requires communication, such as a reduction, all of a sudden it's not as easy anymore as to just put it in a for loop or put in add threads around it. In the case of serial processing, we'll have to use an accumulator. If we want to make a threaded, we'll have to use an array of accumulators, which can be tricky if you have to deal with multiple NUMA zones. If we want to vectorize it, we'll have to decompose our loop into a vectorized main body, a serial loop. And on the GPU, we have to do something completely different. Not going to go into details because I'll do so later. But the summary here basically is that if we want to make parallel programming more accessible, we'll have to both make it easier in order to more simply be able to express your algorithms for parallel hardware, and make it more portable such that you don't have to do it times and times over for different hardware. And the argument I'm going to make is that we can do this in Julia, at least to some extent, and KernelAbstractions.jl is a package that's crucial for doing so. But before I can go into kernel abstractions, I'll have to give a small primer on GPU computing, because kernel abstractions started as a GPU programming package. So yeah, I mean, the origins of it are still visible in the APIs and the way the package works. So at a very high level, if you compare a GPU chip with a CPU chip, you can see that the CPU chip has far fewer cores, but the cores are beefy, large. They have their own control infrastructure, their control logic, they have their own caches, while on the GPU side, we have far more cores, but the cores are not independent. They share cache, they share control infrastructure. And this results in GPU threads being cooperative. They have to work together because they share circuitry. And they're also lightweight because the amount of control circuitry that's dedicated to GPU threads is, in general, much smaller than it is with a CPU. And in order for these threads to cooperate with one another, the programming model we use decomposes threads or organizes threads in some kind of hierarchy, where you can look up the number of a thread, and based on that number, you can see whether a thread is adjacent to another thread or whether it's executing on a different multiprocessor. At the top, we have the grid, and the grid encompasses all threads that are being used for a single kernel launch on a single device. And now within the thread, we have multiple blocks. And a block of threads is guaranteed to be executing on a single multiprocessor. Recall that my chip's GPU has 40 such multiprocessors, so we'll get a similar amount of blocks being executing. The advantage of that is if we know that a thread is executing on the same multiprocessor, we know that we can use the cache memory that's resident to that multiprocessor. And this is essential for efficient communication between threads. And then below that level, within a block, we have groups of threads that are executing the same code at the same time. Those threads are organized in a warp, and it's typically 32 to 64 threads at once. And they are literally executing the same instruction. If you don't do that, performance will tank completely. And in fact, to avoid that, and in fact, to force you almost to execute the same code on these threads, GPU vendors often use a programming model that's called SPIMD. It's in the same taxonomy as MIMD and SIMD. SPIMD, single program, multiple data, means you have a single scalar program of instructions that will be executed over multiple data by different threads. And this contrasts to traditional threading on the CPU, for example, where for every thread you can freely choose what instructions it will execute. This is pseudocode. What the vendors want you to use is this, which is C++, where, well, it's not as nice. So the logical first step here is, can we try to avoid C++ and do this all in Julia? And this was actually the origin story of all this work, where we initially wanted to start writing code for GPUs in Julia. And Julia is a great language for this, because on the one hand, it's a high-level language, which means that it offers greater productivity than what low-level languages like C or C++ does. But on the other hand, it's a carefully designed language that's compiled. And that's essential for executing code on the GPU, because again, remember, a GPU has very lightweight cores. It's not good at executing arbitrary code. You cannot run a bytecode interpreter on a GPU and expect it to function well. And this is where Julia's design comes in. So Julia has been designed from the start to be a language that's not just compiled, because you can try and bolt a compiler on top of any language. It's designed in such a way that it compiles down to very efficient machine code. You can see that snippet there on the left, where we have some very high-level sum over heterogeneous tuple, and nonetheless it compiles down to a sequence of 6 instructions. And that's pretty magical, and that's thanks to the design of Julia. The fact that we use machine-native types, such that you don't have to deal with arbitrary precision integers or floating point numbers in your generated code. The fact that we use multiple dispatch, allowing us to keep our function definitions small and easily analyzed by the compiler. We also use type inference to propagate all the type information we get from a call throughout the function. And then using that type information, we aggressively specialize and devirtualize function calls, such that in the generated code, you get fully resolved static calls to other code, possibly even inlined, instead of having dynamic calls at runtime. And then tying it all together is us handing over that nicely typed, high-quality compiler IR to LLVM, which does its magic and generates very high-quality machine code. And this has allowed us to retarget the Julia compiler and all of this machinery to the GPU, where we can take similarly high-level operations and compile them down to machine code for the GPU. In this example, PTX code for the CUDA backend. CUDA backend was first, but nowadays we have a whole bunch of backends. AMD GPU.jl for AMD hardware, obviously. One API is a recent one for Intel, Metal for Apple, and then OpenCL.jl for any other accelerators that supports per V-code. And even though we have a whole bunch of backends, the design philosophy that we use is fairly similar, where initially we want to make it as easy as possible to start with GPU programming, without taking away the flexibility that you may need to implement something at high performance. And to illustrate both of those, one of the elements, for example, of making everything easy to use is us having put significant effort in simplifying the installation. And this sounds trivial, but any of you who's tried to install CUDA on Python know how tricky it can be to get a fully functioning GPU-accelerated setup. Whereas we, thanks to Julia's great artifact system, make it possible to simply install CUDA.jl, import the package, and then we will automatically discover what kind of driver you have to install, because you still have to install the NVIDIA driver. That's the only piece we cannot automate. But we detect everything, we detect which hardware you have, and then we automatically download the toolkit you need and install it locally. And the same applies to the other backends. OneAPI.jl actually only needs Linux. In the case of Intel hardware, we're even able to download the driver. Metal.jl only requires Apple, doesn't require Xcode or anything, and so forth. Similar things applies to all of these backends. So making it as easy as possible and helping with that is also some crucial simplifications to the programming model. So for example, in Metal, and this applies to most GPU backends, you typically in C and C++ have to look up a device, you have to instantiate a command queue, you have to compile your kernel and submit it to the command queue. So there's lots of boilerplate to get started. And we try to take as much of that boilerplate out of your hands, doing it implicitly, automatically, behind the scenes. So in Metal, basically, after importing the package, you can do add Metal of a function, and it will run on a GPU. That's it. But if you need the flexibility, we still have the API wrappers to get your own device, instantiate your own device queue, command queue. You can still use all of the flexibility you need. Okay, so that's the setup. Once you have things set up, you want to write code for the GPU. And for that, generally, we offer three levels of abstraction: the application level, the array level, and the kernel level. Crucially here, all of these are implemented in Julia, meaning if you're doing something at the application level and it's slow, or you want to customize it, you can, within the same language, write your own array operations or even optimize at the kernel level within the same language. There's never a need to resolve to using C and C++. The application level is the highest level, where, for example, a library like Flux might have this magical GPU function you can throw your model at, you can throw your data at, execute stuff. It's on the GPU. Convenient, but not particularly interesting for this talk. The real magic comes when you're using the array abstractions. So every of our GPU backends has an array type. In the case of CUDA.jl, it's the Q array type. And that type serves a dual purpose. On the one hand, it's storing and managing data because it's being stored on the GPU, and you can use it to upload to the GPU, download from the GPU. And at the same time, it's also a vehicle for dispatch, being able to dispatch to GPU implemented or GPU optimized functionality. For example, here calling the sign broadcast on A or calling the sum function on A will make it dispatch to something that we have implemented for CUDA GPUs. And in general, we try to implement as correctly as possible all of the array interfaces that are common in the Julia ecosystem. Here the examples are the view, the matrix multiplication, scalar multiplication, and so on, all the things you expect. And this makes it easy to take code that you've implemented previously on an array type on the CPU and port it to the GPU by simply changing the array type. Wherever possible, we try to implement with NVIDIA's libraries. Like the random.jl standard library is implemented using current, linear algebra is implemented using cuBLAS, and so on. And this is because in general, the vendor libraries offer unparalleled performance that it's possible to match in Julia. It just takes lots of effort to re-implement this functionality. Up until this point, this is all nice, but this exists in other languages as well. What makes Julia stand apart is the array abstractions that are based on the JIT. We call them higher order abstraction. And that's a mouthful, but it basically means an abstraction that takes another function as one of its inputs. The canonical example is the map function, because the map function, you pass it an anonymous function of yours that performs the element-wise operation. And behind the scenes, we're composing this implementation of map that we made in our library with the user code of yours, and we compile it down to a specific kernel for your situation. And this is only possible because we have a JIT compiler at runtime. This wouldn't be possible in a C library because C libraries are fully precompiled and you would have a static list of types and operators that are supported. And in fact, this composability is something that's fairly widely used in the whole Julia ecosystem. And this is a bit of a contrived example, I admit, but nonetheless, it nicely shows how we can compose code from all places in the Julia ecosystem, with only one of those being focused on a CUDA GPU. Nonetheless, the result will run on the CUDA GPU with all of the additional functionality added from all of these packages across the ecosystem. Very nice talk by Stefan Karpinski about this, because all of this really is based on the property of multiple dispatch and how this is deeply embedded in the Julia language. But as I mentioned, slightly contrived. So something more realistic is this small snippet of code I took straight off of Discourse a couple of years ago. It's a simple linear regression model where we define a loss function, gradient, derivative, a training function, then we initialize some data, allocate some data, input, output, weights, bias, and so on, and we run it in a loop. Porting this to the GPU is literally as easy as simply switching the array type. And I'm not going to argue that this is the best way to do machine learning on a GPU, far from it, but at least it shows that it exposes some of that hardware that's normally hard to use in a very convenient manner. It allows you to at least get some benefit from that very powerful hardware nowadays everybody has, but has been so hard to reach for many of you. And of course, in your application or in another case, it may be that some of these operations are implemented slowly or maybe not implemented by us at all for the GPU. But luckily, you can then resolve to the kernel programming level, where you can, again, within the same language, implement your own kernels. And if we go back to the vector addition example, where we have the simple vector addition implemented in CUDA.jl compared to the one implemented in CUDA-C, if you compare both, you can see all of the aforementioned simplifications of the host code, but the kernel level is suspiciously identical. And this is on purpose, because we figured at the point that you start writing your own kernels, you care about performance, you care about flexibility. So you want to be able to use all of the features that the GPU has to offer. So the focus on the array level is simplicity, ease of use, easy to get started. And the focus on the kernel level is, let's get you all of the nitty-gritty details to get all of the performance out of the accelerator. And this also conveniently makes it easier to port code that you previously implemented in CUDA-C, which was typically in the form of kernels, to CUDA.jl. We do sometimes change the programming model slightly. For example, in metal.jl, normally all of the indexing intrinsic are arguments. We change that to function calls. With Intel GPUs, you normally have to use a parallel version of C++, not particularly nice. So we similarly rephrase that in terms of scalar SPIMD kernels. And this gets us pretty close to portability, because all of these kernels use the same programming model. The only difference is some very minute vendor differences in naming or some very small things. So gets us close to portability, but not completely yet. But I do think I can argue that we made it much easier to get started with the whole GPU programming stack, both by simplifying things and by providing these reasonably powerful JIT-based arrays that often obviate kernel programming. And of course, avoiding these vendor differences is the point where I get to introduce kernel abstractions, which is the library that makes it possible to write truly vendor-agnostic GPU kernels. And for some history, kernel abstractions was started by Valentin Shrevi for the Oceananigans.jl project that's part of Clima. And it was originally called GPUify loops. And as the name reveals, it was a way to take loop-based code and make it run on the GPU. And you can see in a simple example there, there's an add loop in front of the for loop, and you have to specify both the iteration domain and then the GPU indexing function that would be used, which also implies that this would actually not be portable across GPUs. The main use case here was to make it possible to run GPU code on the CPU, such that half of the raw power that a supercomputer has doesn't go to waste. And the other disadvantage of this is that loops are really inflexible. It's fine for embarrassingly parallel operations like vector addition, but as soon as you do something more complicated like the reduction, loops are not great. So the second version, called Kernel Abstractions, was a bit more conservative in design. It retained, for example, the host-device split, where you have the host code launching kernels that run on the device. It goes back to a SPIMD programming model, which are the scalar kernels, where every thread has a single stream of execution. All of the front end became completely portable, and all of the vendor-specific stuff is put into backends. And there was an integrated CPU fallback, making it possible, if you don't have a GPU, to at least run that code on the CPU. And again, going back to vector addition, comparing it, you can see on the left-hand side the CUDA.jl implementation, and then almost verbatim on the right-hand side, only some switches between vendor-specific stuff to some macros from kernel abstractions. Looks extremely similar, and as a result, this may be underselling kernel abstractions a bit. So to illustrate better, let's go for a slightly more complicated example, where instead of the embarrassingly parallel vector addition, we do a proper reduction. And this is still highly simplified, but the main idea is that we use shared memory to communicate between threads. So initially, we're going to have all threads load an element into shared memory, which, remember, is the memory that's part of the shared multiprocessor that a single block executes on. And then we have this loop that at every iteration drops half of the threads, and the remaining threads are going to reduce its value with one of the values of the other threads. And it's being looked up in shared memory, which again is shared across all threads running on a single block of a GPU. If we do this a couple of times, removing half of the threads at every iteration, at the end of the loop, we only get a single active thread. And at the first element in our shared memory, we get a fully reduced element, which we can then write back to global memory. And this is still hugely simplified. This doesn't deal with non-power of 2 length inputs. This doesn't deal with reducing over multiple blocks. The real implementation is significantly more difficult, but at least it does demonstrate the main idea of a non-trivial GPU kernel. Implementing this in kernel abstractions is mostly the same. but we now have some additional macros which I can tell you about. So the macro-based DSL is one of the parts of kernel abstractions. You can see in bold the different macros, and I'm not going to explain them all. That's not the best time spent here in this kind of talk. If you're interested, you can look them up in the documentation. But the two most relevant ones are, of course, the index macro, which lets you look up the number of the current thread in the hierarchy. And it's nicely abstracted. You can request different granularity of indices, either a global index, so the number of the thread within the grid, the number of the thread within the block, or the number of the block within the grid. And all of these numbers are required for some kind of algorithms and to optimize the communication between threads. And then you can also, Julia specifically, ask different kinds of indices. It can be a linear one, which is a single one-dimensional number, or it can be Cartesian, which is n-dimensional. And an n-tuple, which is just the tuple equivalent of a Cartesian index. And then the corollary of that is the group size and the range macros, which let you query the size of the block and the size of the grid. And then on the host side, we have a fairly minimal API, where here you can see we allocate some data using CUDA.jl, we launch it using kernel abstractions, and then we fetch some data back. And this may be curious because, for one, the backend is not hidden, so how is this portable? Well, again, this was a purposeful decision where we want to retain, we don't want to stow the backend away. The backend and the way you allocate data is still device specific. Practical reasons being that we don't want to have kernel abstractions depend on everything, but other reasons are that allocating data is often highly platform specific. Some devices have unified memory, some devices have zero copy memory, other devices have, it's just a huge flavor of ways to allocate data, and it would be hard to generalize that in a way that offers users all performance. But the other big reason is that this retains types, and types are great in Julia because you can use that with dispatch to drive from one implementation to another. And this can be useful if you notice that one implementation performs better, say on the CPU, than others which do on the GPU, because we advertise portability, but not necessarily performance portability, which is a completely different area. It's much, much, much harder to advertise performance portability. So it can always still be possible that your one implementation performs better on certain platforms than the other. And for that, having types in the equation is really useful for you to be able to dispatch to different implementations. Another noteworthy thing is that compilation is explicit. You can see here that we compile our reduce function by calling it, we pass it the backend and some additional arguments, and then we invoke it separately by calling the compiled object. And this is relevant because by passing additional arguments to the compilation, we make it explicit that you can specialize on values. For example, here, if you can see, my reduce function is invoked by the backend, but it's also being passed the length of the data, which makes the workgroup size static. And as a result, the add group size will not return a runtime number, but it will be compiled, specialized for the size of the group. And this makes it possible for that whole loop to get unrolled completely, which on the GPU is often crucial to get any performance. And then finally, the operations are task ordered. Kernel launches normally are asynchronous. So you call them and they immediately return even though the GPU is still computing in the background. If you then fetch the data, it may be possible that you should have had to wait on it, while in our semantical model, we made that implicit. Everything that's executed within a Julia task is implicitly ordered. So you can just fetch the data and you'll be guaranteed you won't be reading data that's still in progress. That's convenient, and it also makes it possible to do concurrent execution on the GPU, which is if you have two tasks of an expensive compute function. For example, this function here does a matrix multiplication and broadcast and fetches the results, so it's computationally expensive. And if we want to run that function on different data twice, and we do so with add async, we indicate to the driver that the execution of those two functions can actually overlap. And in the profiler, we can actually see that the matrix multiplication of those different tasks is being executed in parallel on the GPU. So I think with this, we can reasonably say that we made kernel programming portable. But the big question is, are people using this? Of course, one of the big users we have is Oceananigans, which was the one reason that kernel abstraction was created in the first place. And they've been used to great success to implement a very high performance, high resolution ocean simulation model, which has also been deployed successfully on significant hardware. Using MPI.jl, it's been deployed on Perlmutter, a supercomputer from NERSC, with hundreds of A100s. And nowadays there's even a Gordon Bell attempt based on this code. So this is successfully being used by in a real life setting. Another example user that you may have gotten in contact with is diffiqgpu.jl, which provides GPU-accelerated ODE solvers used by lots of people in the SciML ecosystem. And this is actually the prime use case for kernel abstractions that we're envisioning nowadays. The library that's using to accelerate functionality and offer that in a convenient way to users, rather than maybe users writing their own portable kernel code. And there's a bunch of libraries doing exactly that. So the whole GPU ecosystem itself, GPU arrays, accelerated kernels, and Dagger for distributed execution, all of which are currently being based on top of kernel abstractions. And there's a whole slew of domain-specific libraries as well. In fact, funnily enough, if we look at the reverse dependencies, the dependence of kernel abstractions, there's about 100 direct ones and almost 1,000 indirect ones, which is 9% of the entire Julia package ecosystem, which is a lot. Didn't expect that. But for kernel abstractions to become even more successful, yeah, we have to move past GPUs. GPUs aren't everything. So let's see how we support other hardware. And as I mentioned, kernel abstraction does have a CPU backend, and it's a fairly straightforward mapping of this SPIMD code to threaded code with for loops in it. So we use threads to parallelize over blocks, and then the threaded operations within a block are put in a for loop. Fairly straightforward mapping. But as it turns out, there's lots of problems with it. For example, what happens if we synchronize? Because if we synchronize, all threaded operations have to wait before moving past the synchronization point. And with for loops, that doesn't work. So what we do is we split the for loop. At the synchronization point, we split the loop. We have a for loop before, we have a for loop after. But that has issues, because that breaks scope. If you define a variable in the first for loop before the synchronization point, it won't be able to get used after the synchronization point. So for that, we have some band-aids, which is add uniform and add private, to hoist data outside of the for loop, such that it can be safely reused across the synchronization point. And that's bad, because, I mean, it's a band-aid, and the icon's there for a reason. We don't want to do this. Normally, that's not required when writing SPIMD code, so it shouldn't be required in kernel abstractions. And it even doesn't fix everything. Conditional synchronization, if you put the synchronization in an if block, it's allowed. I mean, with some caveats, but it should be allowed. It's not allowed by the CPU backend. Similarly with early return, where a thread just stops executing, is under some conditions supported by some backends, not by the CPU backend. So we basically realized, well, that supposedly straightforward lowering of SPIMD code to threaded and vectorized code is not so straightforward at all. So we decided to look for alternatives, and we found POCL. POCL is an open source project by Intel and a university in Finland, I think, which provides an orchestration layer to improve interoperability and performance portability of OpenCL code. And what makes POCL interesting to us is that it does contain a whole SPIMD compiler. So it has all of those analyses that we would need to figure out how to deal with synchronization points in threaded code and how to emit vectorized code from that. And it also contains a CPU backend, so we can just reuse that. And we did. We spent, over the last year and a half, some significant time in reviving OpenCL.jl in order to be able to interface with POCL. And we improved our SPIR-V backend in GPU compiler to be able to emit the IR code that is required to properly send kernels to OpenCL. And it works. The next version of kernel abstractions, or the next major version of kernel abstractions, will have a POCL backend. A POCL backend that will be built into kernel abstraction, so it will be lightweight, no heavy dependency on OpenCL.jl. It will support all of kernel abstractions. We will deprecate add uniform, we will deprecate add private, we will support conditional synchronization and early return, and it will directly use Julia arrays, so it simplifies greatly how to work with accelerators. And hopefully it will also improve performance. But we've yet to see that. So this is bound to arrive in the next 0.10 version of kernel abstractions, which will probably then also become the 1.0 release, hopefully by the end of the year, maybe early next year. But now that we have revived OpenCL.jl, we can actually use a full-fledged OpenCL backend and use it with a huge variety of OpenCL drivers, because there's more than just GPU OpenCL drivers. There's obviously Pockle with all of its other backends you got to see on the initial slide. But there's other fun backends. For example, there's Rustical and Zinc, which are two projects based in the Mesa graphics library, also an open source graphics library. And with Rustical and Zinc, it's possible to retarget OpenCL on Vulkan drivers. And one of those Vulkan drivers is, for example, the one in a Raspberry Pi, which contains a Broadcom GPU with a Broadcom Vulkan driver. So with that, we can actually run Julia and we can run kernel abstractions code on the GPU that's in a Raspberry Pi, which is pretty sweet. So the only thing this requires actually is a sufficiently recent Vulkan driver, and even so recent that it's not packaged up in the latest version of Raspberry Pi OS yet. So if people are interested in it, please reach out, please help out. Look at it as a proof of concept, but it does show that there's lots of opportunities to expanding the reach of kernel abstractions. And finally, I also want to add with some limitations, because I mean, we're not perfect. There's limitations to how we're doing things. And one example I'm going to use for that is something that somebody asked me to port a while ago, which is a Frobenius inner product, which other than that, I'm completely unfamiliar with. But it does consist of a transpose, a matrix multiplication, and a trace, where the trace is taking the sum of the diagonal. And if you implement it like that, using our GPU backends, using kernel abstractions, you get all of these operations executed individually, which is a waste, because the matrix multiplication is dense and the trace only takes the diagonal. So there's lots of computations that are inefficient. Same with the transpose and the matrix multiplication, but for that at least we use the type domain to try and lazily encode the transpose and then make the matrix multiplication aware of that transpose not having to happen. But that's not a scalable approach. That's not something you can do for every operation. So in fact, using the type domain for that, in my opinion, is slightly questionable. Especially so because this can be optimized in a completely different way. We can do, instead of a dense matrix multiplication, we can do an element-wise multiplication, which is much, much cheaper, and then just take the sum of that. Or in fact, we can go beyond and represent this whole operation as a simple dot, which is much cheaper to compute. The problem is that because of how we encode this and because of how the Julia compiler not having this global visibility of the host and the GPU code executing in tandem, it cannot optimize it together, and all of the operations get executed in isolation. And the typical response here is, well, if this is performance sensitive, try to fuse it together yourself or try to optimize it yourself, which is one of the limitations of the stack. And this is also an area where I get to introduce Reactant.jl, because the goal of Reactant.jl is being based on MLIR. It makes it possible to retain that global visibility, because now we compile at the level where we invoke the Frobenius inner product and not at the level of the individual operations, which is great because you don't have to fuse together stuff manually. You don't have to implement your own kernels. You can keep it all declarative. It's also reasonably portable. MLIR, which Reactant is based on, support GPUs, CPUs, TPUs, and also distributed execution. So that's great. And you get to benefit from all of the optimizations that are implemented in MLIR. The problem is that Reactant is a little bit experimental. And the problem to me is also that now you're all of a sudden at the mercy of the compiler doing this kind of optimization for you, which in this case, ironically, does not happen. So my Frobenius inner product is still being implemented as a matrix multiplication, then a slice which gets a diagonal, and then reduction. And I know it says dot general, but that's just how matrix multiplication is represented in MLIR. Nonetheless, it does show how the compiler now has a global view of all these GPU operations that have to be executing in one go. So if the compiler were slightly smarter, or if somebody implements this specific reduction, it would be possible for MLIR to optimize this completely away, which is something we are probably not going to be able to do easily at the kernel abstractions level. And for more details on this, there is going to be a talk on MLIR, so I don't want to steal too much of that content. But I do want to show that even though reactant can be an alternative, having been shown at this, it is not, because both approaches can perfectly well coexist. Because MLIR supports so-called raising of IR. So when you have a kernel that's being queued by kernel abstractions, for example, here I'm invoking my vector addition kernel, and then I'm doing another element-wise addition. You can see by MLIR raising the LLVM IR back into MLIR, you can see in the resulting graph that we have both operations fully detected, such that MLIR can fuse these together into a single kernel invocation. And this is actually what the Gordon Bell work on Oceananigans is working on, because Oceananigans does use lots of kernel abstractions, and with this, all of that code can get reused and nonetheless optimized by MLIR. So it can perfectly well coexist. And this brings me to my conclusion that Julia has a whole slew and a whole variety of ways to program parallel accelerators, many of which are very powerful, such as all of the backends that we have, allowing you to write high-performance code for your GPU, initially in a very easy way by using the arrays, but also with all flexibility that you would normally have in the low-level toolkits. Nonetheless, if you need to do this in a portable manner, you can use kernel abstractions, which at this point in time has great support for all the GPUs that we support in Julia. Soon it will have a proper CPU backend, but with all of the potential that OpenCL brings us, may extend to many more GPUs. So again, if you're interested in targeting any specific accelerator, do reach out for us. And beyond that, we now also have reactant.jl, which may open up a whole new area of optimization and implementation. So for that, definitely do check out the lightning talk later today in this room on reactant.jl. And with that, I'm at the end of my slide deck. So thank you for your attention.
Thank you for this very nice talk. I finally understand everything about GPU. But recently, there's been a new package, very interesting for people who are not very familiar with the internal of GPUs, which is accelerated kernels. Can you tell us how it fits in the landscape, please?
Yes, so accelerated kernels is a package that's based on kernel abstractions. So it implements a whole variety of high-performance array operations implemented using kernel abstractions. For example, it implements a sorting function, it implements a reduction, it implements a variety of these. And the focus of those implementations are to get all of the performance that the GPU has to offer, while also providing lots of flexibility in terms of the algorithms that are being used in the inner loops and so on and so forth. And then to make the picture complete, next to that we have GPU arrays. GPU arrays is similar, but with the focus on implementing the array interfaces that Julia has. For example, the sort and the reduction function APIs that we have in Julia are much more constrained than all of the flexibility that accelerated kernels has to offer. And in order to unify things, we're moving towards basing GPU arrays on top of accelerated kernels. So accelerated kernels gives you the primitives with all flexibility and all performance, and then GPU arrays reuses those, or will reuse those, to expose them in a Julia array interface compatible manner. And both of those are entirely nowadays based on kernel abstractions as a way to implement GPU kernels.
Hello, thanks for the talk. Also really impressed at how the package has evolved recently. Just wanted to ask, what do you think is the current penalty on GPU versus just raw CUDA C++?
On the generated code, there's virtually none. It's been a while since we evaluated this, but back when we did a straight up comparison of Rodinia kernels, which is a parallel programming benchmark suite, implemented both in CUDA-C with C++ compiled with MVCC, and implemented in CUDA.jl. And there was no performance difference. And the only performance difference was in differences in compiler backend, because back then the compiler backend used by MVCC was slightly different than the compiler backend used by LLVM and the open source stack we are using. NVIDIA is actually moving towards using the open source stack as well and contributing their changes back to upstream LLVM. So it's expected that the performance difference there is going to go completely away. There are some performance differences on the host level, which is, for example, when launching a kernel. If you do that in CUDA C++, it's a very cheap API call, whereas on the Julia side, we do much more checks and verifications, and sometimes there's some types unstable code in there, which may induce a slight overhead, but it's in the order of single-digit %. And additionally, it's also relatively easy to optimize away, because for that code, you can simply use any Julia profiler and spot, for example, the type unstable code and optimize it. I think the only area where we're significantly lacking to CUDA C++ is the extremely advanced features of the GPU, such as the tensor cores or the more advanced data types. Those tend to be hard to use, and we haven't fully implemented those in Julia. On the other hand, very few users actually do use those advanced features, like programming the tensor cores directly. Almost everybody is going to use the tensor cores through libraries such as cuBLAS. And for that, of course, we have perfect coverage. So we're lacking from some things, but it shouldn't hurt most users, is the bottom line.
And small. Oh.
Yeah, that's right.
Okay.
Thank you for a great talk. I don't know whether you answered my question in the presentation or not. I'm thinking about if you want to use the array interface with the GPU and don't want to write your own kernel explicitly, but suppose you have a function you write using the Julia's array interface, and there are several instructions, several lines of code. Is there a way to say that, oh, all of these lines should be fused into the same kernel? So we'll so is there a way to make Julia fuse these operations into the same kernel without actually explicitly writing out the kernel itself?
So if you're talking about very coarse-grained abstractions like a reduction and then a broadcast and then a sort, for example, which are the highest level of abstractions, there's no way of fusing those together with some caveats. But if you're talking about, for example, multiple subsequent broadcast operations, which map very closely on the thing that you would put in a kernel, then at that level, you can use, for example, the lazy broadcasting package. I think it's called lazy broadcasting. There's a couple of packages, lazy something packages, which do expose lazy versions of array operations such that they're traced across multiple expressions and they only get collected at the final point in time. And then we can fuse them together in a single kernel launch. So to some extent, that is some extent being multiple broadcast expressions, that is supported. We can also fuse a broadcast and a reduction, but we cannot fuse, for example, an invocation of a sort function with an invocation of a reduction. Those kinds of fusions are currently not supported.